Welcome to this presentation about the Master Track Plasma and Beams of the Department of Applied Physics, the Eindhoven University of Technology. My name is Richard Engeln and I'm the track coordinator, and I'm also PI in one of the research groups in the track. Now within the track Plasma and Beams there are three research groups: Coherence and Quantum Technology, Plasma and Materials Processing, and Elementary Processes in Gas Discharges. And the common theme within these groups is plasma, also sometimes called the fourth state of matter, after solid, liquid and gas. Plasma is a hot ionized gas, consisting of reactive particles like electrons, ions and radicals. And more than 99% of the known matter is plasma. But this is mainly because close to 100% of the matter in the universe is in the plasma state. On Earth you rarely see plasma occurring naturally. Lightning and the northern lights are examples. But mostly on Earth, plasma is man-made. How do you create plasma? Well, like in going from the solid state to the liquid state, and from the liquid state to the gaseous state, you supply heat to the system. If you want to create plasma, you just have to heat the gas. And in heating the gas, atoms can get ionized, molecules get dissociated and ionized, radicals can be formed. So you actually create a mixture of heavy ionized atomic and molecular species and free electrons. And furthermore, very often, the plasma starts to emit light. But what makes plasma so peculiar is the fact that due to the huge difference in mass of the light electrons and the heavy, neutral and ionized atoms and molecules, the kinetic temperatures of these species is different, which is a unique property of the plasma, namely that this state of matter is out of equilibrium. This leads to a chemically very active medium at relatively low gas temperature. This allows, for example, for processing materials that cannot withstand high temperatures. Now, how does the Plasma and Beams program look like, or the curriculum? Well, first there is a compulsory track course, Physics of Plasmas and Radiation. And in that course you are introduced to the basic concepts of plasma, like Debye lengths, quasi-neutrality and ambipolar diffusion, and the relation between plasma, charged particle beams and radiation. Now there are also plenty of track elective courses, and they are given by the PIs in the different groups in the track, including a few fusion related courses, as you can see here. Now, for a complete overview, you should always visit the Osiris student website. Now, since some of the research in the groups Plasma and Material Processing and Quantum Coherence and Quantum Technology is closely related to, and sometimes even overlap with the research in the NQP track, both groups are also part of the NQP track. And that means that if you decide to choose the Master Track Plasma and Beams, you can still perform a master thesis final project in one of the NQP groups. You then need to choose as track elective the NQP track compulsory course, Condensed Matter at the Nanoscale, and the track elective Photonics and Modern Optics. Now here you see an overview of all the PIs in the different groups that are part of the track. As most of these PIs are also involved in the bachelor curriculum of the Department of Applied Physics, you might recognize some of them if you did do a bachelor in physics at the TUE. Now in the next few slides I will focus on the research that is performed in the different groups in the track, and we'll do that by their mission and approach. Now first, the group Plasma and Material Processing. Their mission is obtaining atomic level understanding of the interaction of plasmas and reactive gases with materials in the field of atomic scale processing. And their approach is studying plasma and surface processes in situ and in real time with a large set of state-of-the-art existing diagnostics, but they also develop new diagnostics for their particular studies. Now here are a few examples of the research teams within the PMP group. They work on developing new applications of plasma in the field of nanoengineering and gas conversion. They study the use of plasma for deposition and etching with atomic scale precision and functionalizing flexible substrates for solar cell applications, to just name a few. Now in their research they make use of optical diagnostics to better understand the kinetics and dynamics of the plasma processes both in the plasma gas phase as well as on the surface. Now these diagnostics are very often laser based and developed and built in the group. Now, the mission and the approach of the group elementary processes and gas discharges are shown here. So EPG is studying the elementary processes in gas discharges. And they do this through a mix of theory, modeling and the development of diagnostics. And their approach is integrating state-of-the-art plasma diagnostics and advanced plasma models. Now they study different types of plasma, ranging from cold atmospheric plasma for example, wound healing, through streamer discharges that mimic natural occurring plasma in lightning, and plasma under microgravity conditions, studying the behavior of dust particles in plasma, and these dust particles can have detrimental effects in chip manufacturing. Now these studies are performed with laser-based diagnostics, like in the group EPG, PMP, and ultra-fast imaging, and are always supported by a strong modeling effort. And all those modeling efforts have led to their own plasma modeling platform called Plasimo. Now the mission of the CQT group is exploiting collective effects in dilute, strongly interacting systems of high phase space density. These can be ultra-cold atoms, quantum gases and plasmas, and high brightness electron, ion and atom beams. Now their approach is both theoretical and experimental, and they use tools including high power lasers, and they use high power lasers and compact particle accelerators. Now they work on new strategies to perform ultra-fast electron microscopy and generate X-rays for imaging biological systems with a tabletop synchrotron light source. But they also develop electron and ion beams for milling features with nanometer precision, and they also model quantum simulators based on ultra-cold atoms and quantum coprocessors. These quantum coprocessors are hybrid quantum classical computing devices. So it's clear the research in the groups has both fundamental and a more applied or engineering signature. The result of the engineering signature and the focus of the groups on valorization is clearly exemplified by several products and tools in which the plasma technology developed at the Department of Applied Physics at TUE is incorporated. And the many links the groups have with industry, some of which can be found in Brainport Eindhoven area. Now, why would you choose for the master track plasma and beams? Well, first of all, you can do research in a highly interdisciplinary field. You can do that research both fundamental and on a more engineering scale. And at the same time, you can become an expert in state-of-the-art experimental techniques and or computational modeling. Furthermore, you can work on the development of novel plasma applications. And last but not least, you are well prepared to become a PhD and will be very attractive for industry in general or for one of the many high-tech companies in Brainport Eindhoven. If after watching this video you have a question, do not hesitate to contact me, Richard Engeln. Thank you for watching.